Hello and welcome to my compiler tutorial series. So in this tutorial series we're going to be making a compiler from scratch in Java, and the language is going to be this. So this is my custom language that I've been developing for a while called Graph, and it's a language designed for physics simulations and games. And I'll just give you a brief demonstration. So this file in itself is called verlet.graph, and it just does a simple physics simulation, verlet integration, physics simulation. If I run this, we get a window pop up, and if I click, this grid of balls will fall to the container. And you can see they sort of react with the container and they collide with each other. And it's just sort of a nice way of testing the features in the language and also just demonstrating what the language can do. So we'll close that. So now I'm just going to give a brief overview of sort of how a compiler is structured. So as you can see here, we have this small diagram, and this just sort of shows you the general pipeline of a compiler. So at one end, we start with the input text. So this is just an array of characters. And the first step is called tokenizing or lexing. And lexing is short for lexical analysis. It sounds more complicated than it is. Really, it's the simplest step. All it means is you're just breaking up the individual text characters into chunks of more significant things. So when I say things, what I mean is there's several different types. There's identifiers, which are things like this vector2, which is a structure name. The int is an identifier, the a is an identifier, so variables, type names, that sort of thing. So anything user defined is an identifier. We've also got punctuation, so anything in sort of this like purpley color is punctuation. There's also some other ones that aren't in purple for some reason, but like the semicolons and the add operators as well are all punctuation. Then we have keywords, so like struct or an if else, while, true, true, false, that sort of thing. And then we have white space as well, which is also parsed out. And that's just so that we can sort of identify if in cases where there's, for example, if you had if true as one word, that would be an identifier, but with a space in between, it's a if statement with a true as the argument. Okay, so once we get through that stage, then we get onto the parsing stage, or sometimes called the syntax tree generation stage. So whilst it's not a true tree in a sort of pure computer science way, it is similar. So what it amounts to is every sort of thing in your program, every higher level structure, you represent as some sort of subclass of a node, right? So in this example here, we've got struct, which is a object, and it has a name, vector2, and a list of fields. And then one of these fields is a variable object, and that has a name, x, and a type. And then that type is another object, another node, that's called literal type, which is of type float. So you can see by sort of chaining and grouping these nodes into arrays, you can sort of represent the semantic structure of your program. Then you can also see here we have another example. So this is a case for expressions. So expressions are actually represented more like a standard sort of computer science tree, or a more rigorous, I'm not sure what the word is, a more correct tree. So you'd have binary operator object, and this is also these are all of type node, or they they sort of conform to a node interface, or they're a subtype of node. But anyway, you can see here this is a slightly high level view. So each of these elements is a node, and you can see here it sort of forms a tree. And you might also notice that actually the order of these is different to the order of these. That's because of operator precedence. We actually want to do the multiply first, then the division, and then the addition. And when we get to it, there's actually an interesting way that you can you construct the tree so that the operator precedence is always satisfied. So we'll leave that. Then you get onto the flattening stage. So I'm not sure if this is completely universal or if it's just something that I do, but in essence, what you're doing is you're de-nesting structure, sort of more complicated expressions. So complicated nested expressions, you need to, in order to get this into a form where you can just do operations sequentially and get the correct result, you need to actually store the results of intermediate operations. So the way that I do this is that I generate sort of temporary invisible variables that store the results of intermediate operations, and then at the end you just put in a variable reference to sort of, in this case, print int. There's also two other reasons why you do this. So another reason is it simplifies your code a lot, because it means that you can just define one way of later on converting, for example, a procedure print int into some bytecode or assembly. And the reason why because you only need to define a case for when it's a variable that it's trying to access, you don't need to consider all the permutations of different cases where, this int may be a literal value, or it may be, or a literal value and a variable. You just say they're all variables, and then they all need to be pulled out in this sort of flattening stage. The other reason, second reason why you do this, is because it sort of allows you to do type checking quite easily, and as sort of in the same process you can also type check, and that's obviously because you're only doing one operation per line. You know exactly what the result should be, and therefore you know the type of each of these intermediate variables, and therefore if these are all correct, then you know the type of D, and then you can evaluate if D matches the type of print int or not. So that's another sort of secondary bonus of doing the flattening stage. Then the last case, or the last stage, is the bytecode generation. So what this is it's taking the series of high level instructions from your syntax tree, from your flattened syntax tree, and converting that into a list of instructions that are much closer to the machine, or much more similar to assembly, for example. So in this, you don't have variables. The variables are converted into like stack offsets. The sizes of things are calculated so that you allocate the correct amount of stack space, and that when things are indexed and read and written to, that they write the correct amount of bytes and that sort of thing. So it's a much lower level than this stage, and also the actual individual instructions are simpler. So for calling a procedure, for example, you don't just say print int of D. You actually have to, for example, push all of the arguments onto the stack, call the procedure, which literally just jumps to a different point in your bytecode, and then runs, starts from there and does the series of instructions of that procedure, and then returns. And then this assign pop is sort of an example of, for example, if you had, this case where, or B, which is get age of A, you'd push A onto the stack, and then sort of the thing on the top of the stack would be the return result, and then you would assign B to that. So you'd pop the stack and assign B to that value. So you can see that in that very simple, or this very simple case, this one line thing is converted into 3 lines. So and sort of the reason why you do this is just because it's possible to run actually even the syntax tree generation, the syntax tree form, but it's very slow. It's then actually also possible to even run this, but it's also quite slow. This stage is actually reasonably fast. It's not quite as good as native, actually writing the assembly and compiling an executable yourself, but it's good enough for our purposes, and I think it conveys like the concepts just fine without having to actually deal with all the nitty gritty of how assembly and x64 works. And then hopefully you run that bytecode through a virtual machine, which is sort of another stage, and then you get your output. So hopefully that was that's sort of understandable. In the first episode, we're just going to start right at the beginning, and we're going to do the tokenizer, and then hopefully we should almost get one stage per episode, but other stages are slightly bigger. So for example, parsing is a little bit bigger than tokenizing, that sort of thing. So anyway, thanks very much for watching, and I hope to see you in the first episode.